So, welcome back. So, we will continue with our discussion with the welding section. So, like we have discussed till the last class about the metallurgical attributes of the weld joint and contribution of the filler metal and parent metal on weld microstructure and also the mechanical properties. So, in this class we will discuss in detail about the weld joint architecture and also the mechanics of weld joint. So, before moving into that, in this slide you can see that there is a differences has been drawn between the different common welding processes with the rate of heat input. So, what are some low rate of heat input welding processes? Those are oxy-fuel welding, electroslag welding and flash welding, and with some moderate rate of heat input welding processes are shielded metal arc welding, flux cored arc welding, gas metal arc welding, submerged arc welding and gas tungsten arc welding. And then there is the last variant, that is which deals with the high rate of heat input. They are like plasma arc welding, electron beam welding, laser welding, spot and seam resistance welding and percussion welding. So, we will discuss about the nuances of these individual welding processes briefly later in this section. However, now we will discuss about the weld joint and its mechanics. So, this schematic and this flow chart shows you about the computational weld mechanics. So, this is a subject of interest. It is one of the analogous topic with the manufacturing processes, and because welding is one of the most versatile technique to useful for generating assembly of different parts or members, and it is very much important to study it often by numerical technique, because you may not be able to subject to post welding analyzing its efficacy and its performance. Then it has to go through the destructive testing, which can cause a lot of time and cost sensitive. It can be time and cost sensitive. So, it is wise to study the joint mechanics, its performance, and also the process parameters which are necessary to create a joint with the desired level of structural integrity and the quality characteristics such as the desired microstructure and properties by computational welding mechanics. So, computational welding mechanics deals with the mostly talks about the solid state of the joint, that means the performance of the joint. It also talks about the thermal effect, when it is subjected to thermomechanical loading, and it also talks about the solidification micro mechanisms that the joint experiences during solidification. So, you can see that several sub segments that constitutes computational weld mechanics, that is the concepts of stress strain, boundary conditions, graphics, computer hardware, constitutive behavior of the weld metal, and also the microstructure and heat transfer attributes. So, as a whole it constitutes the computational welding mechanics. So, now when we discuss about the joint design, design of the weld joint, so then it is important to learn these symbols. So, this is the symbol which shows like weld all around. So, this circle is shown that it signifies that you have to assume that there is a circular body which is getting connected over a plate. So, then weld all around symbol signifies that you have to weld it throughout its periphery. So, this is a kind of symbol which shows which signifies the manufacturer about its applicability for the joint development. Okay. So, this is how the joint is developed. Okay. So, and then there is a P denotes the unwelded length, L denotes the welded length, length of the weld, F is the finish symbol, and this hyphen is the contour symbol, S is depicts the size of the weld, So, I mean for example, if we are talking about a fillet weld between two plates which are placed angular manner. So, then this is basically this is the fillet weld that is generated between these plates which are kept perpendicular to each other. So, then so this is basically the length or size of the, I mean this is the considered as the size of the weld, and this distance, I mean this is, I mean basically termed as the, I mean throat or thickness of the weld, which is generally depicts as T, and capital T here is the specification process or other reference, and this symbol here it shows about the tail omit when reference is not used. So, basic weld symbol or detailed reference is shown by this parenthesis. So, we so now let us move into the, I mean different joint, how they are designated. So, arrow side of a joint is the line, side, area or near member to which the arrow points. The side opposite the arrow side is the other side. Shape of the weld of the can be understood by the manufacturer what kind of weld is desired at that particular place. This is also the way how the weld, location of weld and the type of weld and the shape of the weld is mentioned in the manufacturing drawing of a particular part which is going to be developed. And so, this is this symbol of the hemispherical symbol denotes the weld bed, and this is this triangle signal symbol denotes the fillet joint, and this is a symbol, this trapezoidal symbol denotes a plug or slot, and this is in case of square weld, this is V groove weld, this is bevel weld, this is U weld and J. So, please recall that when we have discussed about several butt welding variants. So, that time we have discussed about the butt welds can be classified in terms of the joint architecture. So, in spite of a V groove, butt weld is not always a V groove joint. It can be of all of this shape, like a typical U shaped, I mean joint preparation, then we call it as U type, I mean bevel, I mean butt joint. It can be also prepared like bevel shaped one, it can also be prepared as the J shaped grooved one. So, it depends on the joint architecture which is needed for that particular application, and also it depends on the I mean the joint strength and also the availability of space that we are discussing, and also the size of the parent metal or the work pieces that we are basically trying to join by via welding route. So, it depends on many of these factors. Okay. So, so here you can see the welding symbol examples are shown here. So, so in this case you can see the weld leg size of 5 mm and fillet weld at both sides. So, here so I mean so you can see this is basically it shows about the size of the weld as 5 mm and it is on both sides. So, both sides of the, I mean this T joint, that is I mean shown here with the help of these triangles, I mean that is this I mean the triangle at both sides of this line. So, this is how it is designated. Number 2 is the intermittent intermittent and staggered 60 mm along on 200 mm center. So, so this can be designated like this drawing. So, you can see these are the right angle triangles which shows the, I mean weldings, that means the welding has to happen on both the sides, but they are not spaced at the same location, they are staggered. And so, you can from this symbol you have to understand that between both the welds, adjacent welds, there is a central line gap between the adjacent welds are 200 mm and the, I mean this length of the weld or the size of the weld is basically 60 mm. That can be understood from this I mean symbols. And then the third one is a leg size of 5 mm and on one side only outside circle indicates the way around. So, this symbol signifies that we need to join around the periphery of the, I mean so the like I have drawn earlier also, the like a cylindrical hollow cylinder which is kept over a plate. So, it symbolizes that there has to be a joint around the periphery of the I mean cylindrical part. Okay. So, this is how we have to designate the weld joint. And then we will consider some simple I mean problems of how we can basically do the joint design. So, here assume that there is a single transverse fillet weld. So, I mean you can see that so this is basically I mean here T is the throat thickness, I mean here. So, this BD shows the throat thickness, S is the leg or size of the weld, and L is the length of the weld. So, L is along the length. So, here L is shown over here. So, this is the length of the weld, this is the leg size of the weld, and this is the throat thickness or I mean thickness of the weld. So, so here if we know the value of the leg size of the weld, then we can quite easily evaluate the value of the throat thickness of the weld. How? Because you can see that here the included angle, because it is a right angle triangle. So, both the other angles are 45 degree. So, then what we can so then if we can calculate the value of sin 45 degree from here for the triangle CBD, then we can see that basically it is the DB by I mean the BC, that means the size of the weld. So, that means DB is equal to small s sin 45 degree. So, that means it is sin 45 degree, we know that it is 0.707. So, 0.707 s is equal to T, that means the thickness or throat thickness of the I mean fillet weld. Okay. So, this is how we can get, and then once we get the throat thickness, we can quite easily evaluate the area I mean of the weld zone or sectional area. So, we just need to multiply it with the throat thickness. So, then it becomes equal to 0.707 into 1. Okay. So, with this, so if sigma T is the allowable tensile stress for the weld metal, then the tensile strength of the joint for single fillet weld is equal to, I mean as we know that sigma T, I mean sigma is equal to load by area. So, that means we have to calculate load, then we have to multiply with the stress with area. So, then it is nothing but sigma T into the area, that means sigma T into the throat thickness T into the weld length L. So, that means T is equal to we know 0.707 S into sigma T into L. So, this is how you are getting this expression for the I mean joint strength, okay, when the tensile loading is applied. And tensile load in case of a double fillet weld is nothing that you have to multiply it with a value of 2. So, then you are arriving at this value in case of a double fillet weld. Okay. So, and then strength of parallel fillet welded joints. So, the parallel fillet welded joints are designed for shear strength. So, consider a double parallel fillet welded joint as shown in this figure. So, minimum area of weld or the throat area A is equal to 0.707 S into L. So, if tau is the allowable shear stress for the weld metal, then the shear strength of the joint for single parallel fillet weld P is equal to throat area into allowable shear stress. So, here we are talking about the joint double parallel fillet weld subjected to shear stress. So, then P is equal to throat area into allowable shear stress, that means 0.707 S into L is the throat area into allowable shear stress, that is tau. And shear strength of the joint for double parallel fillet weld, again it is quite same like we have discussed in case of tensile loading. So, we just need to multiply it with 2 because we are talking about double parallel fillet weld, and the resultant expression comes like this. Okay. So, now if there is a combination of single transverse and double parallel fillet weld. Okay. So, these are the two double parallel fillet weld having length 2, and this is a single transverse fillet weld having length L. Okay. So, the strength of the joint is given by the sum of strength of single transverse and double parallel fillet welds. So, we have already evaluated in case of shear strength of double parallel fillet weld, that is 1.414 S into L into tau. So, that is what is shown over here for the contribution from this double parallel fillet weld, and contribution for the single I mean transverse fillet weld, that is subjected to tensile loading. So, then this is 0.707 S into L1, that is the length of this I mean single transverse fillet weld into the allowable tensile stress, that is sigma T. So, then this is how we can get the total I mean strength of for this single transverse and double parallel fillet weld. So, where L1 is normally the width of the plate which is getting joined with the base plate. Okay. So, in order to allow for starting and stopping of the bead, So 12.5 mm, so 5 is not clear here, so let me write it over here. So 12.5 mm should be added to the length of each weld obtained by the above expression that is shown here. So for reinforced fillet welds, the throat dimension may be taken as 0.85 T. Okay. So I mean, so because I mean, because of the reinforcement that this is considered 0.85 factor is considered. And then now moving on to the another special case of fillet welded joints, that is deals with a circular fillet weld subjected to torsion. So this is a circular fillet weld, then where it is welded all around the periphery of the solid circular rod that is welded with this base plate. So here small d is the diameter of the rod, r is the radius of the rod, T is the torque acting over the rod, that is symbolizes here, small s is the size of the weld, and T is the throat thickness, J is the polar moment of inertia. So as we know from this formula that tau by r is equal to T by J. So T is the applied torque, J is the polar moment of inertia, tau is the shear stress, r is the radius of this circular rod. Okay. So I mean, so here I mean so then from here we can determine the maximum allowable shear stress in this joint, which will be T cross r by J. So J, as we know that these are basically the polar moment of inertia, it is a geometric factor that can be mentioned over here. So it can be further written as T cross d by 2, that is the diameter of the circular rod, divided by pi t d cube by 4. So then finally it comes as tau max is equal to 2 t, that is the applied torque, pi t. So if we know the joint size, then we can evaluate the joint thickness, and we know the diameter of the rod which is getting joined with the base plate, we can very well evaluate the maximum allowable shear stress in the joint that it can withstand. Okay. So with this we can move to the next slide. So circular fillet weld subjected to torsion. So in this case, this shear stress occurs in a horizontal plane along a leg of the fillet weld. So the maximum shear occurs on the throat of the weld, which is inclined at 45 degree to the horizontal plane. So the length of the throat, as we have calculated before, that is 3 is equal to s sin 45 degree, that means 707 s. 0.707 s, and the maximum shear stress tau max that we have determined over here, that is tau max is equal to 2 t by pi t d square. So if we now put on the values, then 2 t divided by pi into 0.707 s into d square. So the which finally comes as 2.83 into applied torque divided by pi, that is 3.14 into the size, leg size of the weld, into the diameter of the circular rod, which is joined with the help of a fillet joint with the base plate squared. So this is how we can determine the maximum shear stress. Okay. And then so here the another case when we are circular fillet weld subjected to bending moment. So earlier case we have discussed circular fillet weld that is subjected to torsion, and this is another design case consideration where it is subjected to bending moment. Okay. So the bending moment is designated here as m. Okay. So then the other things are pretty same, that is d is the diameter of the solid cylindrical rod that is getting joined by fillet weld, and t is the throat thickness, s is the leg size of the weld, and here we have to evaluate the section modulus of the weld section. So as we know that in case of bending stress, sigma b is equal to m by z. M is the bending moment that is acting over the rod, divided by z, that is the section modulus of the weld section. So which will be pi t d square by 4. So please do not confuse with the case of this polar moment of inertia, that is pi t d cube by 4, and here the bending moment section modulus is pi t d square by 4. Okay. So then finally if we put on this value, so pi t d square by 4, so we are arriving at 4 m divided by pi t d square. That means t is the throat thickness, m is the applied bending moment to the circular rod. Okay. So, we have evaluated the bending stress. So, now how, so this bending stress occurs in a horizontal plane along a leg of the fillet weld. So, the maximum bending stress occurs on the throat of the weld, which is inclined at 45 degrees. So, we know how to evaluate the thickness of the throat, as we have done several times earlier. So, S sin 45 degree, S is the leg size of the weld, that means it is 0.707 S, that is the throat thickness, as we have evaluated earlier, that sigma b is equal to 4 m by pi t d square. So, sigma b is equal to 4 m by pi t d square. So, then we can write from here that it is equal to 4 m by pi into 0.707 into s into d square. So, from here by simplifying, we can write that it is as equal to 5.66 m by pi s d square. So, if we know the value of the applied bending moment, that is certainly we do, and then we know the length of size of the leg size of the weld and the diameter of the circular rod, then we can calculate the maximum allowable bending stress the circular rod can withstand, which is joined with the base plate. Okay. Yeah. So, moving on with the next problem. So, in this case it is a long fillet weld subjected to torsion. So, torsion that is shown over here. So, T is the torque acting on the vertical plane, L is the length of the weld, S is the leg size of the weld, and T is the throat thickness. So, here throat thickness is like this. Okay. So, this is the throat thickness. So, which is equal on fillet joint made on both the sides. So, it is a typical example of T joint. Okay. So, you can see from the cross section you can understand it is a T joint, okay, from side view. Okay. So, here the polar moment of inertia J, it is because it is we are talking about two joint here. So, this joint number 1, joint number 2. So, that means polar moment of inertia J need to be multiplied by 2 T L cube by 12. So, then it reduces to T L cube by 6. Okay. So, shear stress how we can calculate, as we know tau by r is equal to T by J. So, that means tau is equal to T r by J, T is the applied torque, J is the polar moment of inertia, and so I mean here I mean r is equal to L by 2. So, I mean that is the I mean total length of the weld. So, that means it becomes equivalent to tau is equal to T small l by 2 by Z by J. So, J we have already evaluated here. So, J is equal to T L cube by 6. So, that means T L by 2 divided by T L cube by 6, that means into 6 by T L cube. So, then I mean we can arrive at this expression. So, I mean so here so this is the small T L cube, this is the small T L cube by 6. So, then we are arriving from here as equal to 3 T L by T L cube. So, then it becomes L square. So, 3 T by small t L square. So, as we already know that small t is equal to 0.707 into S, that is S sin 45 degree into L square. So, then further simplifying we can get the value as 4.242 T by S cross L square. So, this is the value of the maximum shear stress, okay, that this joint I mean double fillet I mean double fillet weld that can be subjected to. So, this much shear stress it can withstand. Okay. So, now we will move into the butt joint. So, this is a typical example of butt joint, that it is a single V butt joint that I have drawn and explained to you on several occasions. So, the butt joints are designed for tension or compression. So, consider a single V butt joint as shown over here, having the plate thickness or also the thickness of the I mean joint throat thickness and also the plate thickness are same here, which is shown as marked as small t, and a small l is the leg size of this is the length of the weld. So, then the tensile strength acting over the butt joint, as we know P is equal to sigma by A. So that's why I mean sorry, this is sigma is equal to P by A. So that's why we can here calculate the strength of the joint. P is equal to sigma A, and area here, as we know that the thickness of the weld into length T cross L cos sigma. So that is what sigma T, that is the tensile load stress that is applied. So the strength of the tensile strength of the joint can be evaluated like this, T cross L cross sigma. Okay. So L is the leg size of the weld, it is generally equal to the width of the plate. Okay. So then if we are talking about double V butt joint, so as we told earlier that based on the thickness of the workpiece materials which are experiencing joining with each other, we may need to go for preparing two V groups in spite of one, because in that case the joint will not be proper. So this is basically the root region where both these plates are very much close to each other. Okay. So this is the I mean the central line of the joint, and above the central line the I mean thickness of the joint is T1, and below the central line thickness of the joint is T2. So in this case the I mean tensile strength of the double V butt joint can be evaluated as P is equal to sigma into I mean A. So that means P is equal to sigma T into L into T, that means T is nothing but T1 plus T2. So that is what is shown over here. So I mean so it may be noted that the size of the weld should be greater than the thickness of the plate. So that is because of the hump that is created at the fusion zone or the weld zone. So I mean this is the hump that is created. So that's why the total I mean thickness of the I mean weld joint is basically higher than the thickness of the plate. Okay. So this is so there is a gap between the thickness of the plate and the total thickness of the weld joint. So I mean this table shows the recommended minimum size of the weld. So if the thickness of the plate varies between 3 to 5 mm, minimum size of the weld should be 3. If it is between 6 to 8, minimum size should be 5. So likewise it is given for minimum recommended size of the weld I mean for different plate thickness, and these are some minimum sizes. Below this size of the weld, then the joint is subjected to fail, and it will hardly have any strength to and structural integrity. So the stress concentration factors for welded joints. So the reinforcements provided to the weld produces stress concentration at the junction of the weld and the parent metal when the parts are subjected to fatigue loading. So the stress concentration factor for different kind of joint configurations like reinforced butt welds or end of parallel fillet weld. So these are the stress concentration factors which are evaluated. So these are empirical values for different weld joint architecture is shown over here. So for any static loading and any type of joint, stress concentration factor is 1. So these different stress concentration factors are only applicable when the joint is subjected to fatigue loading and not in case of tensile loading. Okay. So now we will move to the axially loaded unsymmetrical weld section. So this problem is I mean little bit tougher, and it is basically, but in case of real life assembly we often come across this kind of weld joint. So it is important to understand the mechanics of this kind of axially loaded unsymmetrical welded sections. So sometimes unsymmetrical sections such as angles or channels or T sections are welded on the flange edges, are loaded axially as shown in this figure. So in such cases the lengths of the weld should be proportioned in such a way that the sum of resisting moments of the welds about the gravity axis is 0. So here in this I mean axially loaded unsymmetrical welded joint, the CG lies over here. This is the center of gravity. So consider an angle section as shown in this figure. So here LA is the length of weld at the top, LB is the length of weld at the bottom, and total length of the weld is summation of LA plus LB. Okay. And P is the axial load that is applying over here. A is the distance of top weld from gravity axis. So here this is the gravity axis. So this is the distance of the top weld from gravity axis A, distance of the bottom weld from gravity axis B, and F is the resistance offered by the weld per unit length. Okay. So, then so the moment because as we told that the moment I mean has to be I mean the sum of the resisting moments of the weld about the gravity axis has to be 0. So, that is what we will now mathematically derive. So, moment of the top weld about the gravity axis, that is applied force into distance. So, that means L A into F into A, and then moment of the bottom weld about gravity axis L B into F into B, and then since the sum of the moments of the weld about the gravity axis must be 0. So, then we will I mean so deduct L A L B F into B from L A into F into A, and we will equate it to 0, and which signifies that they I mean they are equal. That means F gets cancelled out when we put it to the I mean right side, and then it becomes L small a into A. That means the length of the weld at the top, that is L A, length of the weld at the bottom, that is L B, and the distance of top weld from the gravity axis A is equal to the length of the bottom weld into distance of the bottom weld from the gravity axis, that is B. Okay. So, now as we also know that L is equal to L A plus L B. So, from this equation and from this equation we can now, so from these two equations we can now write very easily that L A is equal to, if you just put this I mean value of L A into here, we can express L B in terms of small l. So, likewise we can also express L A in terms of small l, that means the total length of the weld, and the resulting expressions comes like this for L A and L B. Okay. So, I mean so with there are some little more problems that we will discuss. However, we will take it up in the next class. So, we are stopping for this class here, and we will meet soon with the rest of the weld design problems. Thank you.